Hello, everyone. Hope you're doing fine. We are going to wait for some minutes now because, there are quite a few people that we need to wait for joining. So, yeah. Okay. So, how you been? Nice. I'm doing well. A bit tired these days, but generally well. Um, have you had a chance to go over the guest lecture? How did you like the Tobias lecture? Do you think do you have some feedback for me to improve it for the next guest lecture or something like that? That's completely fine. Don't waste the opportunity to get the free access to O'Reilly course. At the end of his slides, he provided a link for us to get for 30 days for free of O'Reilly platform. So there are like thousands of courses, books, and stuff like that, even live streams. So it's 30 days for free. I don't know if you have to provide credit cards. Personally, I didn't check it. I'm paying myself like for my O'Reilly account, so I don't know what's like his link providing to us, but basically, like it's 30 days for free. So I would definitely go check it out. And yeah, so you can learn a lot of stuff in those 30 days. No worries. Okay, cool. So today we are going to jump on basically office hours as um, previously, like the week before, Friday, we did go over like introduction to machine learning and stuff like that. But unfortunately, the lecture was not recorded. So the goal of today is to revisit the questions that you potentially have, go over the project, the code base, and maybe some slides. If some of you are still haven't had chance to go over slides and stuff like that, we are going to repeat those stuff as well. So the goal basically today is to revisit like high level overview of the Friday's lesson, answer questions if you have any, plan for the next couple of weeks what we're going to do, and yeah, so just chat. And this will be recorded, so and at in the YouTube channel. So if you had like urge to check it out twice, you will have the opportunity to do so. But yeah, basically that's the goal for today. If you have any like questions immediately, let's go over them right now. If not, I would jump to slides again so that we covered last Friday, repeat certain topics. Hopefully you have some great questions for me today so I can address them as well. And yeah, so how do you like that? Okay, cool. So if we don't have any questions, I would definitely jump to slides. And I won't go as detailed as I was the last time, because the goal of today is not to last for 3 hours or 3.5 that we took the last Friday. It's going to be a shorter session, like 1.5 hours to 2 hours maybe, with the idea to revisit the crucial parts for you to understand, because like we are going to talk of all of these concepts in the upcoming weeks. So obviously, if you don't learn something today, you're going to need to revisit, but it's not to be as crucial as missing something in a week 5, for example. We are going to take this and repeat it constantly, because that's part of a learning process. So yeah, so no worries if you don't catch something today, or we go over certain parts really fast. Just bear with me. In the upcoming weeks, we are going to talk about this stuff even more. Okay, cool. So oh, sorry. Okay. So basically that's the idea was, to start by explaining just what is machine learning. We talked about machine learning as a part of computer science. We said that machine learning does not work without data. So the crucial part, two main parts of machine learning as a whole, is having certain algorithm and having some data that we provide to that algorithm so we can learn from it. And we said that machine learning is nothing else but part of computer science that addresses the problem in this way. So having some algorithms that might learn some patterns from data. Those patterns are different, and that's what we call different learning styles of machine learning, that we're going to go and talk about them in a second. Um, but before we do that, let's talk about the parallel difference, I would say, between traditional software engineering and something that we call today AI or machine learning. So in traditional software engineering, we said, okay, if you had, let's say, a task to build a classification algorithm for cats, you and I sit in a room with your teammates and say, okay, how are we going to approach this? Our boss has this cat here. Let's think about crucial elements or parts that actually represent this cat, so we can abstract those elements and put something in our functions. And we first off started by recognizing those points, and then try to build a code, build functionality around those patterns, so we can actually, when this image arrives, we can detect those patterns in the image. And we ended up like detecting something as ears, like we have a left one and a right one. The same goes for eyes, so we have two eyes, nose, and then the necklace. We recognize those as a like kind of a building blocks of this cat. And when we say, okay, when any image comes into the system, we would run it by those checkups. And for example, each check would check if there is a ear or not. And let's say we just return true or false, and we say, okay, if all of these return true, this is basically the cat that we are trying to detect. So that was basically the highest level overview of traditional software engineering, of how we would approach creating something as a cat detector. There are other ways as well, but this is the mindset. So let's build certain functionality. Let's detect like what are the edge cases, what is the representative part, so we can abstract it with the code. But then we said, okay, what if we receive so many cats, different positions, different shapes, different sizes, and stuff like that? All those things that we built for the cat in the previous slide would fail. So still we have here 2 eyes, 2 ears, nose, mouth, potentially a necklace. It's not visible in these images, but none of those would be detected with our functionality, because those were built for specific cat that we actually saw in the previous slide, this one. And then, okay, so is this still a cat? It is. And we need somehow to abstract this problem even more and say, yeah, but our code would need to be updated for each image that comes to our system. That's a bit tedious process if you ask me. Like every single cat or every single image, we will first need to say, is this a cat or not? And if it's cat, we need to build those functionality around it as a set of checks for that cat in particular. And that becomes not scalable really fast. So each image is different. Imagine that, for example, this cat is shifted by just a centimeter right, that's a completely different image. Because if we build per coordinates, let's say I is here and not here, well, those two coordinates really dictate that image that we are currently looking at is completely different. It is as well. So that's something that we could solve with traditional, but it would take a lot of time. And we introduced machine learning here and said, this is actually the problem for machine learning. We have some data. That data might be thousands of images of cats. We don't want to write code for each of those cats or new cats, because our goal is to recognize any cat, So we get that data. We say, here is mathematical model, or here's my machine learning model algorithm. Just learn to say, is it a cat or not cat based on these images? And that's what machine learning does. It takes a lot of data, tries to find the patterns in it, like ears, necklaces, eyes, positions in the image, variations that we provided, backgrounds as well. Like, for example, if you have a data set of cats and dogs, it's most likely to have more dogs outside playing in a park, but cats are more inside on a couches, on whatever. So that's basically something that machine learning will abstract and learn those patterns. And when you provide an image just of inside, it's most likely a cat for that machine learning algorithm. Okay, so that's what machine learning does well. It takes a lot of images and tries to replicate that knowledge to the new knowledge that or to the new images or data that we are trying to provide. And none of the algorithms are going to work 100% of the time. There are going to be cases where it's not certain, it's 50-50, it's 70-30. In this case, in this example here, is 90-10. But no algorithm out there will be 100% correct. So obviously there will be mistakes. It's the question of how many mistakes are we going to make. And that's why we try to learn all the techniques that we are going to talk about to find the best model or the best technique that works for our data. Okay. So then we asked our questions, why now? What is happening right now that's so important for us to learn machine learning? Machine learning was not introduced recently, like a couple of years ago. It basically was present in our lives for decades now. Like even in the 60s, AI and some techniques of machine learning existed back then, where people tried to make an algorithm or a machine that would basically take an input and provide some output based on that learning. But now we are in a really interesting moment of a time where we generate so much data, even so that we don't have energy or capacity, human capacity, to actually process and get value of all of those data points that we currently generate as a civilization. We generate so much data that I think, like based on the last statistics, it's more than 95% of world data is never touched. So it's basically just data, but just 5 of those percents of that data is actually useful to us. Like there's a lot of logs, there are a lot of like unstructured data, text, images, and stuff like that is never used. The other aspect of that is we are currently in a stage where hardware becomes more and more cheap every day. So if you don't have a laptop, you can always use Google Cloud that we are currently using for these lessons. You can always use something as a cloud provider, GCP, AWS, Azure, whatever you like. And there are a lot of providers such as OpenAI, Hugging Face, and stuff like, many others, H2O, that provide models and the platform to deploy those models for basically like cents in some cases. So you can work with world-class models for really cheap. And that's why now, like, you can build crazy interesting products just by knowing certain amount of machine learning these days. You don't have to be experts. You're not going to be researchers in deep learning, DeepMind or OpenAI sometimes, but you can build crazy products with the knowledge that you currently have and that you're going to acquire in the upcoming weeks. Okay. So Just to put everything in perspective, this is how much data we generate. Like, we know about gigabytes, terabytes, even petabytes we heard about. But we as a civilization per year generate this much zettabytes. And not only one, but 16 of those per year. So we are so far ahead of everything that we can actually process in a timely manner that it's crazy. Like, we only maybe 5%, most 10%, but like more than 90% of data, world data, is never touched. And that's where we need more and more machine learning or data engineers, data scientists in the world to get some sense of the data. So it's crazy. Yeah. And I mentioned to you that machine learning as a technique is there for us to get leverage from some data and try to learn some patterns from it, like whatever that pattern might be. And based on those patterns that we are learning and trying to recreate, we have these techniques. We have supervised, unsupervised, semi-supervised, and reinforcement learning. All of those has their own spot in our lives, and every single technique that we currently have here, we are going to cover in the throughout the course. But basically, they have their own place. Sometimes you're going to opt in for supervised, sometimes for unsupervised learning and stuff like that. It really depends on the requirement of the project and the requirement of the data set that you currently have. So, what is supervised learning? And today, and this Friday, well, we covered already supervised learning last Friday, but we're going to talk about that part of learning today and this Friday. But before I continue, there is a question. It is stored. It is stored, but generally they're like sometimes so the question is, when I say it's not being touched, do we mean by not even storing the data, or just like never accessed, or just being too complex? So that's a great question. It is generally stored, like not all the data. We don't have, like, generally, I don't know who has that much storage, but I think we have across all platforms and stuff like that in the world. But it is stored mostly. People are generally like not like leveraging the data in many of the cases, and there are many of the businesses. Like, most of my clients are generating tons of data that are not complex, but just right there, either not structured at all, or just plain like didn't have capacity or knowledge to get value from the data. And many businesses that I'm currently working with never heard of opportunities that machine learning provide. Like, they heard about AI and stuff like that because it's a kind of a hot topic right now, but they actually never gone more deep than ChatGPT and said, okay, but what these techniques can do for my business. And for example, recently I started working with a company in real estate. They didn't even hear about the opportunity of price optimization. So obviously they can find optimal prices for their square meters or square feet, whatever, wherever you come from. And generally, like, they didn't even understand that that is a possibility to leverage like outside data, external data, internal data, history of data, and start optimizing prices per like neighborhood or whatever. So they didn't even hear about that. And they are in the business for, I think, more than 15 years now. And that's what I mean. But that data is not touched. Like, they have the data, they have a lot of it, but they didn't even use it. Recently, I worked with a company in for onboarding people or helping people to get immigration to a certain country. And I work with that company who works with immigrants to actually file in the application, like learn certain like stuff about the whole process, stuff like that. They labeled everything and collected every single data point from the beginning of their existence of the company, which is 10 years in the past. So for the 10 years, they recorded every meeting. They had notes for every meeting, selected, done well, and everything, structured, everything. every client that they've processed in the past 10 years, they have a notation about it. They have like every single document, single document that's even classified or non-classified with non-personal information, so they can expose to the new employees that they can learn from the data. And they have a crazy amount of opportunities in that business because there is so much data, but they didn't even touch. So that's where we are currently. Like, there are so many businesses that we can help with these techniques, but they are not they don't have the knowledge of the opportunity that lie ahead. Okay, so supervised learning. When we say supervised learning, it's mostly common. Like, most common way of machine learning is supervised learning, and to some degree it's the easiest to solve. Okay, what I mean by that is we have some data that basically is already pre-labeled. Let's say we have 10,000 images of cats. We already know that those images contain cats. Okay, so when we provide that data to machine learning algorithm, we are expecting that algorithm to learn that those images have cats in them. So we already know what we want from that machine learning algorithm. They're trying to basically collect the data, map to those labels, and that learning function that we are trying to produce is that machine learning algorithm. And when a new image comes, we would like to know what it sees on that image. Is it a cat? Is it a background? Is it a dog or something else? Okay. So basically, that's the supervised learning. Supervised learning branched out to two different, I would say, ways or types of data. One is regression and another one is classification. Today we are going to talk about classification. This Friday we are going to finish classification and continue with regression. So classification is what I just explained. You have some images, there is like certain class specific thing that we are trying to learn, like is it a cat, dog, background, whatever. And then there is a regression. Regression is an example of price optimization. So what is the like price of this house based on every input of the neighborhood, of like the size of the house, how many rooms and whatever. Like all those patterns are there. We just say, based on these patterns, generate the price of this house, or based on the user experience, years of experience, education, background, history, whatever, propose the salary to a new employee. So there are companies out there that are using these types of algorithms, simple regression models that provide certain insights to HR people what salary range to provide to that new employee. So basically that's what happens. And that's supervised learning. So some data, some label, try to learn, like bridge between those two. Then we have the unsupervised learning. Sometimes we have tons of data, crazy amount of data, but we don't have any labels for it. Like, we don't know what we would like to learn from this data. So what should we do? Well, when you have that type of a problem, you have tons of data, like these samples here, that does not represent anything here at the moment. You would like to learn groupings. So what are the pieces of the data that are connected together in somehow? So those, like for example, clustering is a type of unsupervised learning. We're going to talk about clustering next week, I think. Yeah, next week. So basically, when we talk about clustering, you provide the data and say, just find clusters of users, groups of users that have something in common. You don't know what you expect. So you basically expect some groupings. You didn't say based on what, based on or how many. Sometimes you can just give a data and say, learn whatever you like. Machine learning in that sense will try to find patterns and say, okay, these groups only represent women above age of 40 with salary this big, and basically that's one group. The other group might be football fans, male in age of 20 to 30 with college degree or whatever. So you can go as deep as possible depending on the data that you currently have, but unsupervised learning is there to provide those groups for you. And some of the examples of this application might be customer segmentation that we are going to use for this type of learning. And for example, you can optimize marketing campaigns based on this knowledge. And there is a fraud detection that is really common among in the banking system there, where you try to find those outlier moments where people are not actually in any group by themselves and they did something wrong. So you can detect fraud in that sense. And that's called anomaly detection as well. Then you have semi-supervised learning. Semi-supervised learning lays between supervised and unsupervised learning. So you have some model that is trained in the same way as for supervised, but you have, let's say, 1 million images of cats or dogs, but you have only 10,000 of them labeled. When I say labeled, for only 10,000 of those, you have human labeler go and say, in this image, I see a cat, in this image, I see a dog. So 10,000 of those, maybe 5,000 of cats, 5,000 of dogs, you only have 10,000 labeled. Crazy amount of data is not labeled. So what you would do, you would basically train the machine learning model. You would provide some insight to it. Hey, this is basically already labeled data. Try to learn something from it. And then you're using that knowledge to extrapolate to the unlabeled data and try to label it or try to predict on top of it based on the knowledge from the labeled data. And on that knowledge, you can basically label the whole data set, and then you either provide supervised learning or your solved task, and that's it done. The last thing that we have as a way of learning is reinforcement learning. Reinforcement learning is not that often used in production. Well, not in smaller companies. In big companies, like for example Google, use reinforcement learning for optimizing their electricity bill in data centers. One startup in France used this to train a robot and stuff like that. But generally speaking, like if you go for machine learning route and start working as either data scientist, machine learning engineer, or whatever, you're rarely going to utilize reinforcement learning in your day-to-day job. And reinforcement learning is imagine that you're training a dog, as you can see here in the image. So you have a dog, which is your algorithm. In the world of reinforcement learning, that algorithm is called an agent, as you can see here, the word here. Then that dog can perform some actions: sit, run, lay, turn, whatever. The environment, which might be you, will take the note of what the dog does. Like for example, you say sit and they run instead of sit. You say bad dog, or don't give a reward. A reward might be a treat. And that reward tells the dog whether or not they done a good job or not. So in computer world, that reward might be -1 or 1. So you're simply rewarding your algorithm with -1 or +1. And the algorithm itself will try to replicate that good behavior and discard the bad behavior in the learning process. So you can teach a robot to walk, you can teach a system to drive a self-autonomous vehicle. You can do a lot of stuff with reinforcement learning, but it's really difficult to train, much more difficult than like supervised learning, for example. And in production, like most companies are seeing reinforcement learning as a risk because we don't know, like in most cases, what's going to be the quality of that. So they are mostly opting for something as a supervised learning, sometimes unsupervised, but reinforcement learning generally not. That's a great question. So we have a question: is ChatGPT a kind of reinforcement learning example? So ChatGPT is combination of reinforcement learning and supervised learning. What I mean by that, it's trained based on supervised learning method, like I won't introduce those words just yet, but the algorithm itself is kind of a trained as a supervised learning. But then what they did when they finished that initial learning method or training method, they sat down, like not they, but they hired people like you and I, and we sat down at the computer, and then we basically chat with algorithm, and we basically say, is this output from ChatGPT good or not? Basically, we train the algorithm by saying, hey, this output is bad, don't produce this don't produce this output ever again for this question. So like I think hundreds of people sat down in front of ChatGPT before it was deployed to us, and they sat down and like just rewarded the algorithm positively or negatively based on the output they gave. And throughout that learning process, it was able to produce semi-consistently quality outputs that we currently see today. So it's not still perfect, as you can see. Like sometimes it's a really bad answer, but sometimes it's quite okay. It really depends on the training process. But yeah, so ChatGPT is not trained completely on the reinforcement learning, but one part of it is. Well, okay. It's amazing question. So we had a question. How do we make sure that we don't have a human bias not fed during a reinforcement learning phase? So okay, human bias will always be in machine learning. The question is, how much are we willing to accept it? So in most cases, your data set is going to be biased. Like in most cases, the data sets that we currently see, like for any big AI system, like Google Translate, Google Search, ChatGPT now, or whatever, like Midjourney, any model basically, is trained on the data sets generated in the West. So you have a Western culture, people with their pre-biases built in them collecting the data set. You don't have to have people collecting, like personally sitting down and collecting data set. You can scrape the internet, but internet is full of biases, like racial bias, gender bias, political bias, whatever type of bias that you can imagine. It's accessible to the algorithm via the internet, like Reddit, Google search, websites, random blogs and stuff like that, because our preconceptions and pre-biases that we live with, that we are not actually giving that much of attention to because we live with them, are built into our models. The job of machine learning engineer or a company who is going to introduce this algorithm to the world for their system is to try to eliminate those biases as much as possible. Like OpenAI done a pretty okay job with those in the past. Like DALL-E model, when they released the DALL-E 1, it was really biased. Like when you write a firefighter, it would be only male, white. When you write a teacher, only male, white, older. When you write not a teacher, a professor. A teacher would be only white, young girls. But then when they changed that, because they had so backlash because of that on Twitter, they now built on top of the DALL-E model set of filters that guarantee you like at least one black woman or black man, at least one woman or one man in the output and stuff like that. The ChatGPT has similar system to that, but it's still not perfect. Like you can bypass it with different techniques because you're working with text, but generally you will always have biases in your model. It's as I said, it's only the question of how much are you willing to accept the amount of bias there. Yeah, but amazing question. It's a really big problem, and we definitely like need more and more research in that area as well. Okay, so everything said, like whatever type of machine learning model that we opt in, the goal is simple: understand something from the given data. So we try to replicate those learnings from the data, patterns that we saw in the data set. And throughout that pattern, throughout that learning, there are a couple of outputs or outcomes that our model may receive. One might be the overfit, the other one underfit. Both of these outcomes are something that we don't really want to see. So when you train the algorithm, and we had an amazing question as a prompt to this, you don't want to be on overfit side, because like you're providing some data that you currently collected, and that algorithm, if it learns everything by heart, like basically memorizes the data set that you gave to it, it will only know that data set with the noise, with biases, with everything that pre-exists in that data set. But the goal is not to replicate the training set. The goal is to abstract it, and then as well as good as possible, to replicate those learnings to the new data set that user provide to us through application, through, like, for example, Google Translate. You don't want to learn only the set of sentences that you are given. You would like to have something that actually comes from us that we try to translate. On the other side, we have a model that did not learn anything. It might be that it just started training. It might be the other case where we have too simple model. Like, for example, you use only one linear regression model for the data set of, 10,000 parameters. All of these might lead to underfitting the model. Underfit means that, as I said, model does not learn anything. It does not capture any relevant information from either data set, and it performs worse on training as well as on test or unseen data. So basically, those two cases are extremes you don't really want to be in, and both of those extremes may occur in some types of form while you train an algorithm, but we are going to experience that in the future. But now, when we mentioned that, we need to say, okay, what is actually the goal of machine learning? And that is to generalize or to perform as good as possible on unseen data. So data that will come to us in the future from users, like from any user that you might expect. That's basically what you're going to see. And that being said, you don't want to be on either side, on overfit or underfit. You would like to be on the sweet spot in between those two extremes, that your model actually learned quite enough from the training set, but not so much so it can actually produce good results on unseen data, on the test set, if you want, labeled here with this orange dot. So that's basically the goal of any machine learning model. Whatever you choose the technique is, that's the goal. So now that we cover this basic introduction, let's talk about like what actually goes into building a certain ML pipeline. But before we continue, do you have any questions for this part? Okay. If you don't have any questions, let's continue. Okay. So there's quite a lot of moving part when we talk about machine learning pipeline. We have some features, then we have that machine learning algorithm that ties everything together. We have some predictions that came out of that machine learning algorithm. We have something that we call loss function. In some literature, you will call this a cost function. And then we have correct labels if we are talking about supervised learning, so where we already know what we expect. Okay, so what are these moving parts? First, just to uncover one type of machine learning algorithm, which might look something like this, where you have a mathematical formula that is basically n times x1 plus k times x2 plus b equal y. It looks, a bit ugly at the moment, but actually it's really beautiful. And this simple formula can solve and provide a long way in the result side. We'll talk about and break down every single part of this in a second, but just for you to bring it more down level from machine learning algorithm to certain more practical. So M, K, and B are parameters of this model. Those are going to be changed through learning. X1 and X2 are features, and Y is something that we want to predict. That is our target. Like, is it a cat or a dog? So just keeping that in mind, you don't have to remember all those things just yet. So, sorry, this is just a simple example of a data set. We have a data set that somebody provided to us, like that looks like this. We have gender for every single subject in this data set. Everyone is measured in a height and their weight. Weight is in kilograms, height is in centimeters. Sorry if you're using something other than metric system. Apologies for that, but for you, these are just numbers. Then we have some goals. Our goal is, by providing to the model gender and height, we want to predict weight. Okay, so we have gender, we have height, and then we say we would like to provide to predict weight. So when the input is male and 188, we would like that model to say it's 97. So let's break this down. Instead of having those features here, now we have one sample from our data set. So you have gender and and the height, male and 188. Those are called features. The model that we saw previously done something like some calculations of these two parameters, male and 188, and predicted 80 kilograms. But then we have the correct label, which is 97. So obviously we are missing 17 kilograms. Our model is not working as correctly as we would like, because it missed for quite a lot if you ask me. So that being said, let's go and uncover this model now. And now we saw the same things that we've seen before. So we have m times x1 plus so on and so on. Now, important thing is to remember that we cannot change our data. So our data, male and 188, stays the same. So that's something that we already know. Somebody gave to us. That's it. That's basically real information. We cannot change that. But now, how can we actually learn something to correct this wrong label wrong prediction of 80 kilograms? So we can't change the data. We potentially could influence the prediction, but how? If we dig into this formula, we see that 80 is dependent variable. Like, based on the left calculation, we are getting that. So 80 is not changeable directly, but indirectly. So we know that data is fixed, male and 188, and then we have these three numbers, M, K, and B, that are some random numbers for us now. And those are things that machine learning will learn in the process. But how? Well, that's where the loss function comes into play. Loss function is there to say how off our prediction is. In this case, we have 80 kilograms as our first prediction. Then our loss will say to ask our model and say, okay, but how off are you? And the model will say, well, I predicted 80, the correct was 97 kilograms. I'm off for 70 kilograms on this particular male. And then loss would say, okay, but you need to correct that. Let's do something about it. Obviously, this is not the only sample in your data set. You have many more. We calculated the loss for the first one, where we provided male and 188, where the weight was 97, predicted was 80 kilograms, and obviously the loss was 17 on this sample. And because we are not working ever with only one sample, you need to calculate the loss or the difference from the prediction to the correct label for every single sample in your data set. In this case, we have about 10 to 15, I don't know how many we have here. But if you had 10,000, you would calculate loss for 10,000 samples. Every single sample has some loss dedicated to it, and the total loss is when we sum all of those together. So total loss for this data set is 165 kilograms. I just summed all of these losses together. Okay, so basically that's our total loss. Now that we have that information, we need to influence somehow those numbers that we said that we can change, M, K, and B, so our loss should go down. Obviously, that's our loss. You know, we would like to have loss of 0. So basically, every single time that model predicts something, it's exactly spot on that what we expected. That's never gonna happen, but we want to be as close as possible to 0. So in this case, our model has M, K, and B. So 3 numbers that we would like to change somehow according to our loss, in respect to loss, so they are going to improve over time. In this case, the mathematical thing that we are doing in the background is we are taking partial derivative of each of these parameters in respect to loss. So how much M, K, and B are influencing total loss. Then we get that gradient and basically correct the value of M, K, and B and repeat the process. We are repeating that process many, many times. So every time we are checking the loss for every single sample in the data set, checking if we improved as a total loss, and correcting values for M, K, and B, so we get closer and closer to 0. That's the point of machine learning. This what I just explained, is whole machine learning in a nutshell. So whatever model you use, most models that have some parameters inside of them are going to repeat this process the same, basically. Just so you know, ChatGPT has more than 3 parameters. In this case, we have M, K, and B. ChatGPT has 150 billion parameters. Okay, 150 billion numbers, these M, K, and B, that need to change somehow in respect to loss to give us that chat that we currently have. Okay, so we are currently working with really simple model. It's going to explode really fast, no worries. In 2 weeks, we are starting to come close and close to creep onto ChatGPT. But just remember that ChatGPT is still trained the same way that I just explained. We have some loss, we have some parameters, we have some data that we cannot change, and you would like to reproduce the exactly thing that you would like the user to see. Okay, cool. The whole process that I just explained is called gradient descent. gradient descent basically takes like the gradient of each of the numbers in respect to loss, and then we check whether or not we need to decrease it or increase it, that number, so our loss goes to 0. So basically the gradient will say, okay, in what direction you need to change this number m, k, and b, so you're reaching here the point where the change is basically constant or 0. So we are repeating this process, and every time we are getting lower and lower in the sense of a loss, and every time we are approaching this moment where we are calling that we are either in local or global minima, where all the parameters in the model are constant, or sorry, not constant, but are not changing that much, and our loss is not decreased that much anymore. So we found a sweet spot for all the parameters in the model, so we can perform somehow constant predictions. So just repeat this process for finding for m, k, and b numbers, and that's basically repeated in the cycle. Okay. Before we continue into classification part, do you have any questions? Okay, if you don't have any questions, I would continue to classification, and if you remember something, just shoot. Okay, so we explained that classification is a part of, or a way that we teach machine learning to recognize some patterns through data. We said that for classification to work, you need to have both data and the labels or targets of what you want to achieve with that model. Okay, so to do that, we need to jump to code. So it's the first code sample for us. The code is already pre-written because from the last session, and this code is already shared with you in our Notion document. So if you want to follow along, or you already found this notebook, it's going to be the same. So I won't change it. That's basically it. Okay, so first off, we are working in the environment of Google Colab. I will zoom in a bit. If you need more zoom to the text to recognize better what's written, just tell me and I'm going to zoom more. Okay, so basically we are starting with a project where the idea of this project is to take the Titanic data. It's a really famous data set from machine learning community. There are a couple of data sets that everybody, when starting with machine learning, will go, like Iris dataset, Titanic, MNIST dataset, CIFAR10, and so on. So there are many of those small predetermined data sets that people are generally using to teach algorithms or learn machine learning at the beginning, and then they are switching to more and more advanced data sets in the future, which we are going to follow along in this course as well. So for today's session, we are going to take pandas to work with data, then NumPy to work with mathematical operations like computation on top of the data. Seaborn is generally visualization library, but I found out that you can load the data set with Seaborn. Matplotlib is to create graphs. Generally, we will not use this, but if you want to visualize some parts of this data set, you can do that with Matplotlib. And then here is sklearn library or scikit-learn, which is used to perform machine learning parts of the whole project. We are going to explain every single piece of this when the time comes to it. So don't bother learning that at this stage. So whenever starting with a machine learning project or data science project, the first step is to load the data set. Sometimes it's going to be really difficult. Like I've worked with the projects where I needed to get the data from at least 15 different websites to put everything together, align different languages, different features and stuff like that, so I can start working on pre-processing that data. Sometimes it's going to be provided already to you, like a folder with images. Sometimes it's going to be an CSV file or an Excel file or whatever. And in the best case scenario, where you're just experimenting, it's already online, already known as a Titanic dataset, and you can just go and download it through a well-known library. And that's basically in a single line of code. So you don't have to care about those loading stages that are actually real world needed. This dataset can be found on Kaggle. If you don't know what the Kaggle is, it's a big website for machine learning data science community where people are sharing their competitions. Companies are actually paying a lot of money for good competitions, and you as a data scientist are working on those competitions to earn money, and actually companies getting like solutions from you. So basically they're getting the value by hosting the competition. There are tons of data sets, and for every single data set that you find, there are some code samples that people already submitted their solutions or their way of thinking around the data set. So whenever you start working on a certain project that we are going to recognize in this course, you can always refer to Kaggle as a source of truth, in a sense of like ideas and ideas and inspiration to start working on your project as well. But yeah, Kaggle is a great resource. Use it whenever you can. Okay, so let's back to the code. Whenever you load the data set in this form, it's called Pandas data frame. Pandas data frame allow us to filter out the data, remove the data set, change the values and stuff like that in a similar manner as you would with SQL dataset. So basically, as you can see, here is the whole data set. We have 15 columns, but before we continue, let's make a quick pause of, let's say, 3 to 4 minutes, maybe 5 minutes, just a short break, so we get refreshed and come back to continue with the code. How's that sound? Okay, great. So see you in 5 minutes. Okay, cool. Um, so do you have any questions before we continue? If we should wait a couple of more minutes for everybody to come back. If you're fine, we can continue, and then we can jump on the questions after everything at the end. Cool. So basically, when you start loading the data set, by default, it's going to be in a sense of a data frame. As I said, data frame allows you to quickly check the data, explore the data that we're going to do in a second. You can go further and filter out the data and stuff like that. Basically, most things that you are able to do in SQL, you can do in Pandas data frame as well. However, there are some limitations, like Pandas does not actually work that well when you have gigabytes of data. It's mostly okay for small data sets and small files. But just keep that in mind. Obviously, for the starters, you won't go and jump straight to the 4 or 5 gigabytes of data sets. But just keep in mind that Pandas is not that good optimized for larger data sets. Okay, so our data set, first off, we need to see what we have as a part of data set. We have a column survived that we're going to actually use to predict. So this is our target column, and based on everything that we have as information about each passenger, we would like to see if they survived the Titanic or not. Then we have P class, or the class of their ticket. Then we have gender, which is basically male or female, age. Then we have I think these siblings. Yeah. So then we have fare, embarked, like the location of embark, who. So basically, who is the same as gender. So we are going to talk about how to handle that. Um, is this adult male or not? Then deck, embark down, alive. Alive is the same as survived, and alone. Are they alone or not? That's the data set that we currently have. Just for your note, this data set is not 100% the same as the one at the Kaggle. So people who built the Seaborn library, they changed this library a bit, like removed some columns, added, for example, this alive column. Like there are certain columns that you don't really need, and they added for some reasons, maybe to visualize it better. But generally speaking, like if you compare two data sets, don't be alarmed. There is some difference to it. Generally, the task is same. We want to predict whether they survived or not. So the first step for data exploration phase is to just print out the 5. This is an optional one. You can print the whole data set, but basically, yeah. After that, you get the columns. So columns here just state what information for each patient we have. So you can find columns here. This is mostly for you to find out whether or not you see correctly, like all the information in that data set. As I said, those 2 steps are optional, but good to have just them here at the beginning. Okay. For some reason, my mouse stopped working. I don't know what's happening with my mouse. What? I don't know. Okay. Something weird is happening with my mouse, and I can't figure it out what it is. It's actually connected right now. I connected it to the monitor, so it's charging right now, but I don't know why it actually provide this feedback. I don't know. But yeah, okay. Let me try to interact with the page in a different way. Okay. I can't scroll. Like basically block out of the mouse. Yeah, I don't know. Weird. Let me try to. Yeah, something is weird. I unfortunately I can do anything with the mouse. It's maybe I need to buy a new one. Okay, sorry guys for this. I don't know what's happening. No. Unfortunately, like I'm at my desktop, but only this mouse. Like, yeah, I don't know. Basically, don't know what's happening, what's going on. Hmm. Okay, let's try again. But yeah, so if you go, oh, okay, repaired it. Nice. Sorry for this. Okay, cool. So these two steps are optional, as I said. They are great to have them because, like, as I said, just to visualize what's actually going on in a data set. Sometimes you will change something, or sometimes you will like to create a copies of the data set because you need to either work with it or compare to some other changes that you're going to make in the future. Now this step is really important for us. It's detecting whether or not we missed some data, some information is in each column. So missing information is really tricky to have in a production data set, and you need to address it. Either remove it, remove the like entry, remove the whole user, remove the column, fill in the data. Like there are a lot of ways to fill in the information that is missing. But sometimes, as you can see, for example, here, we are missing age. You can't fill in the information about age except like going to external resource and finding out like what was the age of certain person on board on Titanic. Like I can certainly go and put the mean or average of the age column to every single person that is missing right now. The deck, for example, is missing 688 entries. So for that column, you don't have enough information to fill in even if you want to. So if you're missing more than 35% of the whole column, the best option for you is to just drop that whole column and not use it in your setting. Okay, in this case, we have this information, and you are going to do basically this every single time that you start working with the data set. Check out whether or not there is a certain pieces of information missing. Then I decided to drop some information. So in this case, I'm removing age because I said I can't figure it out the way except going out and like listing a newspaper and everything for every single person and providing the age information. The deck, I remove the deck column. Oh, by the way, for age, because you are missing 177, you can remove 177 entries. Like if you just want not if you want to use the age, but like you're missing 177, you can remove 177 passengers. So from 800 something, almost 900, you would go to on maybe 720, and that's the data set, the final data set that you're going to have. If you're okay with that, go for it. I'm not, because we don't have that big of a data set. Then I'm going to remove alive or who. Those two data sets are here to, for some reason, added externally, but they are basically the same as two other data sets that we currently have, columns that we currently have. One is for survived, which is alive, survived, equal, and another one is who and sex, which is basically equal as well. So you don't need double information. We're just going to remove either one. You can remove sex column and survived and keep like who or alive and alive, or vice versa. So I remove them. Axis is in pandas the way to specify in what direction you would like to drop the information. Axis 0 is basically this, so per column base. Axis 1 is like this. Okay, so I just showed that new information is like this. We have instead of 15 columns, we have 11, and that's the information that we currently have. Then we need to analyze what type of information we have. So as you can recognize here, some information is in text form. We can't directly use text in machine learning algorithms, so we need to perform some pre-processing steps to it. The next step to determine what information we currently have is to call dataset.info. This will take every single column and provide us with data information. Like, is it an integer? Is it an object? Is it a floating number? Is it a categorical value? And stuff like that. So if you refer to this one here, you have numerical features that are like height, weight, age, and stuff like that. Then you have categorical one, which is something that we can group together, like red, blue, male, female, stuff like that. Then we have text features that are generally text, and you have binary features that are either true or false. That's the types of features that you generally have, and you can start exploring like the different ways to pre-process and work with these features. There are a lot of blogs, a lot of like different projects and GitHub repositories that explain like each of these types of features. Then I printed out the head of the dataset again, just to have it visualized here. And what I done here is I said, okay, I'm storing new data to data pre-processed, and calling this function called getDummies. So what getDummies does, it takes categorical features such as male, female, and stuff like that, and creating as many as unique values, columns, where basically all will be like either 1 or 0. So here, if let me I can okay, so let me execute these pieces again. Okay. So this is the data set that I currently had, but if I change this to false, let's just see what we have, and then I'm going to explain. So I'm stating here get dummies, providing the data source, and then checking out which columns we want to convert to binary values. The drop first we'll explain in a second. So what happens here, instead of having the sex column, we have now two columns for that. So sex female and sex male. And you can see what happened, 0 and 1, like where is a male, the other one has 0. Now we have the column for embarked, which has unique values C, Q, and S, and it created 3 columns where if it's an S, it will have 2 zeros for C and Q. So you get the gist. Like, it will create as many as possible columns, as needed columns, where all will be one, all will be zero except one here, which is the true in that entry. And now, because it generated that many columns for every single entry, we currently have redundant information. So that's sometimes okay, but generally not. Here, you know that if it's a 1 here, we should have 0 here. If it's 0 here, it's going to be 1 here. So what drop first does, if we set it to true, it will remove the first column regarding that dummy variable. So instead of having sex female and sex male, we will remove, for example, sex female in this case because it's first from the left, and we will end up only with sex male. In this case, in Bark C, Q, and S, we will remove the first one, C, and just contain Q and S. So let's execute this again. And you can see here that basically what happened. Instead of having 2 columns for sex, we have only sex male. That's it. So that's the data set that we currently have. Now, let's skip this for now. This is the last step for pre-processing, but we don't have to do it. It's for improving the accuracy, so we'll come back to that. Now, the next step, once you have your data set like processed and say, okay, I'm okay with this to be put through my machine learning algorithm, you need a way to separate that data set to two different parts. So why two different parts? Well, because our goal, if we remember, is to create a machine learning algorithm that actually replicates the knowledge from the training set and provides like insights to the unseen data. So we are training on one data that we currently collected, and then we are putting that knowledge and trying to replicate that on unseen data, or the data that is going to come from users in production. But now you are building the model. You don't have that information. You can't ask user to put their data through something that does not exist. So how should we simulate this environment? One way to simulate this environment is splitting your dataset into different subsets. One is for training, which the name suggests you will use to train your model. The other two are validation and test. So the test set, in some literature, you will hear holdout set. That's something that you will like try to create from the data that you currently have, put it under the lock, and don't even look at it until you're ready to go to production. So you're putting that on the side and say, I don't want to look at this data set. That can be 10%, 5%, 20% of your whole data set. It really depends on the size of the data set and your complexity of the task. The goal of test set is to create as representative as possible area for your production environment. So if you are building a cat versus dog classifier, you don't want to put test set only on the cats outside or inside and dogs outside, because some user will come with information such as like they are walking their cat. I know there are people out there in the world that they are walking their cats. So they are taking a picture of their cat in a park. And you need to have cats in the park as a part of your test set just to see how that model would react on user that will send a picture like that. So test set is there to mimic the user behavior as closely as possible. Validation set, however, is there to fastly check how well that model works on unseen data. So you're not training that model on the validation set, you're validating it and trying to like correct it, select the model. Like if you are training multiple models, you would select the one that has the best accuracy on the validation set. But validation is still can be close to training set. It all mostly are, and there might be some data leakage. What I mean by that, like some similar to exactly same images, samples, like users, stuff like that, will be end up in training as well as validation set. That shouldn't be happening, but sometimes it can. But test set, you need to invest the time and money to make sure that it does not have any relevant information to the training set in the sense of the same information. So there is no data leakage. Okay, just so you know, that's basically the splitting part. There are different ways to split the data set. You can read about them too here. But today we won't like create validation and test set separately because there is a work, as I said, to be done to make sure that your test set is actually really well defined. So for today, we're just going to split into two sets, training and validation, and basically do call it done. But in general, like when you start working in production areas, you would like to have the test set separate to do validation. Okay, to achieve this, we'll use a function from sklearn called train test split that takes your features, then takes your targets, and then you specify how much of the data you would like to have for testing part, and then what is the random state. So random state is really, really important, not only for the course that we're currently doing, but when you want to go back to your code and then rerun the train test split function, because it's randomly selecting and you don't specify random state, sometimes you will get inconsistencies in your accuracies. So like make sure that you're using random state, any number. I put 505, but you can put 1, you can put 0, -1, whatever. It's just a state for you to know that you're always generating the same splits of your data set, so you can continue. Okay, here I'm splitting. Let me. Okay, I need to execute this. Okay, let me execute this first and then execute this. No worries about min-max scalar just yet. We will explain that in a second. Okay, so I'm going to execute this, and I created this xtrain, xtest, ytrain, and ytest. Xtrain is piece of features, so your user information like age, gender, and stuff like that for training. Then ytrain is your targets like survived or not survived. Okay, so the first algorithm is called k nearest neighbors, or k nearest classifier in this case. Before we execute that, let's learn about that algorithm in a second. So this is the first algorithm that we are going to cover for machine learning. There are many that you will alongside accumulate and learn about. So once you start applying them in the real world, you will have a basically tool set of algorithms that you know, and you can compare and basically, find the best one that works. So this is the example data set. The example data set has like dots such as orange and blue. Let's say the orange one represent oranges and blue one represent plums, let's say. So you have that data set. They are like scattered around this space in this way, and you get a new new dot that you would like to determine whether or not it's a plum or it's an orange. So let's see how this function actually, how this algorithm actually functions. So first off, you as a machine learning engineer, you need to define by hand the number of neighbors, our parameter k. That's why it's called K nearest neighbors. K stands for number of neighbors that we are monitoring. That number is going to be determined in multiple ways. We are going to explore them today and and this Friday. But the idea of K nearest neighbor algorithm is to introduce this notion of hyperparameters. You, as a machine learning engineer or engineer who works with machine learning parts of the project, most cases the pure machine learning algorithm will be bad. So you need to modify it, change those hyperparameters that are not trainable, they're determined by hand, and they change the behavior of your algorithm. So just keep that in mind. The second step is when we determine that K, we get a new point and measure the distance between that new point and every single point in our data set. Okay, so just let it sink. We are measuring the distance between that new point and every single point in our data set. We are doing this with either Euclidean distance or Manhattan distance. The problem with this data set, the problem of this algorithm, that it needs to store the full data set in memory so it can actually compare the new point to it. So it's actually really memory intensive if you have large data sets. Then we will take the K closest points to the new one based on that distance that we just calculated. And what we do then next is check out which classes they are coming from. Like, are there plums or oranges? And we get how many of each class we have in those K closest ones. Like, for example, we need to have at least like 3 to 5, like K equal to 3 or 5. It should be odd number because for voting power, so obviously one class will be like more present in that closest amount of points. So we are just taking and checking what is the number of classes, and we are just assigning that class that has more points in the closest K. That's it. That's the whole KNN, how it works. So let's see visually how it works. So we get the new point, which is a silver one here. And we check out and say, okay, this is whatever. We maybe know already that it's a plum, but let's check out by the algorithm what is going to be. So we measure the distance to every single point in the data set. That distance is, for example, Euclidean distance. This is the formula for Euclidean distance. So, for example, if you have, I don't know, the size of a plum and the color intensity, you can basically decrease those two, square to find the distance, and then root of that. Then we find the K closest ones. We say, let's say the K is 5. So these circle ones are K closest ones. And we capture the number of classes in those K5, the 5 closest ones. So we have 2 blue ones and 3 orange. And by that notion, we get the new point being the orange. Okay, that is basically how this algorithm functions. So there is nothing fancy here, but it's considered machine learning and it's a stepping stone, so we can go more and more advanced in the future. That's basically it. Whenever you start exploring like algorithms and stuff like that, you will always start from the beginning. Like, you'll always start from the simplest one and then build on top of it, because like sometimes you will be pulled to test the best algorithm that you know, but sometimes the simplest one actually solves the problem. So start from the simple one and then build upon it. Okay. Most algorithms that we are going to use are going to be one-line code. So you don't have to worry about implementing that logic. But if you want, I do encourage you to do so, because the algorithm is not that complex. And when implementing that in pure Python, you'll get sense of it on what actually is happening in the background. So here we are calling k nearest neighbor classifier, setting up the k nearest neighbor equal to 5. As I said, like that's our starting point, and when I execute this, I'm ready to train it. So the training in sklearn always start with .fit, and we are basically providing our x train and y train, and basically we have a trained algorithm. At this point, it's time to make some predictions, and then we calculate the accuracy. This Friday, we are going to talk about different ways to measure the accuracy or the results of a trained model. Accuracy is not always the good metric to follow. We will explore why. So there are precision recall, F1 score, and some other fancy stuff that we are going to talk about, like R2 score, and many more for regression. But today, let's focus only on accuracy, just to see what we have. So, it's not norm, it's X test. Okay, so once I made this prediction, I got the accuracy on unseen data of almost 73%. So we are 73% certain that we have okay predictions. Like, for example, in 73%, we will guess right with this algorithm whether or not somebody survived based on all the information we have about them, like based on gender, based on the starting point of their road trip, based on the age, fare price, and stuff like that. Okay, so back to our normalization stuff. Sometimes in the pre-processing world, you will need to normalize the data. What I mean by that is, as you can see here, fare is some crazy high. Like scale of fare comes from like 0 to 512. I know that about the data set, so I know that, but you can see that other ones are only 0 and 1. So what happens in most cases, this fare being like the largest number can pull the decision from that algorithm towards them because the value is high. It does not mean that it is actually important, but it's actually high. So to give equal importance to all features at the beginning, so algorithm can properly learn from the data, we can normalize it or scale it. So what we mean by that is basically providing like scaling, for example, min max, which brings every single feature, as you can see, between 0 and 1. So instead of having from 0 to 512, we have this fare, for example, from 0 and 1 as well. So all the numbers that we currently have are working from 0 to 0 to 1. And now we can potentially work on the same scale. So let's see if we improve the accuracy of KNN when we just do that. So instead of like replacing this, I'm going to call this other, where I just instead of normal X, I'm providing this X norm, and I'm calling X train norm and X test norm. Let's make here, and just remember this accuracy so we can compare. So let me write it here. Accuracy not norm. So if I call like this, I get even worse accuracy. So that can happen. Like sometimes normalization being like performed on the data that you just starting out, we get worse and worse accuracy. Okay, so basically I didn't train it. Maybe, yeah, I didn't train it. Okay, but sometimes it improves. So what happened here, I tried to test it on the algorithm that was not trained on the same dataset. So that being said, like if you start, for example, to deploy this algorithm, Canon in the production, and that let the user like put data through it, and you train it on normalized data, but then you put normal data to it, like not normalized, your accuracy will be low, 43%. Okay, that happens because you're not using the same processing on your input data. So if you deploy this algorithm, you will need to deploy this min-max scaler, this one, as well, besides that algorithm. So you need to deploy two things, your KNN, k-nearest neighbor algorithm, and your scaler. So once a new user comes and provides their data, you need to normalize the data with this scaler, not a new one, this one. So you're basically trying to do the same thing that you've done here in the production as well. Okay, so that's basically it for that we covered in the last session. Next session, we'll go into logistic regression. We're going to cover more ways to test your algorithms. So that's going to be interesting. And once we are done with logistic regression and properly testing your algorithms in different ways, we're going to switch to regression and speak about linear regression, predicting models, not logistic, but polynomial regression, and actually working with testing regression models. And with that, we are concluding the part of supervised learning, so we can move to unsupervised learning as well. So that's it. This video will be online on YouTube, so you can rewatch it. Don't forget, the due date for the quiz for this part is this Friday. So this Friday, please submit your quiz. Quiz is about 15 to 18 questions, not so long. And I extended the period for your task, like for your homework coding exam, to the end of the next week because of this mishap of Twitch. So yeah, this Friday, as I said, we're jumping on regression, and this Friday we are going to have another homework for regression as well. Okay, don't forget the Monday. This Monday, upcoming Monday, I will send email with that information. We're having a guest lecture again with Marko Velic. He worked as director. He's working currently as a director of engineering at Photomath, and he worked as engineering manager at Facebook for 2+ years. So he led their ads section on the world level in London. So pretty good leader. I had the pleasure to work with him. So he will talk to us about how to build proper like engineering oriented culture, and how to do that on the scale that he's currently doing. So that's basically it as well. So I didn't limit we have a question about the quiz. So can we submit the quiz only once or have multiple attempts? I didn't limit it. Like you need to provide your email address as a part of the question, or the Discord name. So somebody would like to stay private, they can provide just the Discord name. Like you can use that as many times as you like. I'm only like checking once this Saturday. So Saturday I am checking all the quizzes. If they're submitted once or twice per the same email address, I'm checking that then. So yeah, you can generally. But yeah, so at the end, like only people who are willing to participate in the projects at the end will do. So no worries with that. Yeah, me too. I really like the topic that he proposed. So uh, yeah, we'll have a great time this Monday. Cool, guys. It was amazing to catch up with you today. Thank you so much for being here. And yeah, so meet you this Friday. So if you have always any questions, I'm at Discord, so you can always ask me there. Thank you so much. Have a great the rest of the week.